So in this video, we're going to be talking about chapter 3, exponential functions. So let's start off by talking about 3.1, the nature of an exponential growth. So some things we learned in this section was what an exponential growth is, the properties of an exponential growth. You compare exponential functions with linear and quadratic functions, and you explore and understand finite differences. So let's take a look at our first word problem. So it says a bacterial population doubles in number every day. Bob notices the sample population has 100. So find the population of the first 3 days. So what I did was I just made a table of values for all the first 3 days, starting at 0, which had 100 because it states that in the equation. You just multiply each number by 2 to get the next value for the next day. So it says in B to write an equation to represent this growth. So the base function is f of x is equal to ab to the exponent x, right? So we know that in this case b is going to be 2 because that's going to be the constant factor that's getting multiplied, and a is going to be 100 because that's the initial value. So it's going to be p is equal to 100 times 2 to the power of n. So then it says graph this relation. So graphing is very simple when you have a table of values, and we already created a table of values right here. So it just makes it very simple to plot these points since we already have them. So it's very simple to graph in this case. So it says in D, determine the population after 9 days. So 9 days in this case would be n. And we already have the equation, so it's p is equal to 100 times 2 to the power of n. And so you just sub in 9 as n to get 100 times 2 to the power of 9. And if you put that into your calculator, you get 51,200 as a population. So the next question says, describe the pattern of finite differences. So we just made a table of values again and find the first and second difference of the values. And you don't really see a pattern, but when you start dividing the numbers, so 200 divided by 100, you get 2, 400 divided by 200 is 2. And over even on the first differences, 400 divided by 200 is 2, and 200 divided by 100 is 2. So that is the pattern of finite differences. It's 2. So the next question says, Tina invests in an account that has a 5.5 interest rate compounded annually. How much money is required to grow $2,000 in 5 years? So the deposit formula is A is equal to P times 1 plus I to the power of N, where I is interest rate and N is the number of years. So this is all the given information just from the word problem. So N is equal to 5, A is 2,000, I is 0.05, and P is unknown. So to find P, you just take the equation that's given to us and you substitute all the values in and isolate for the P value. So to do that, you have to add these two numbers to get this, and you divide both sides by 1.055 to the power of 5 to get the P alone. So P is equal to 2,000 divided by 1.055 to the power of 5. And if you put that into your calculator, you get 1,530.27. And then you just write a therefore statement to conclude your answer.